This is the pre-exposure video for chapter 2.4, and we're going to discuss two important classes of limits, infinite limits and limits at infinity. In medicine, science, and economics, interesting things happen around asymptotes, and I'm going to tie in this section how asymptotes can be described as limits, and that's really, we're going to learn a new definition for asymptotes. So let's start off with infinite limits, and the formal definition is on the slide. But, essentially an infinite limit mathematically can be written as the limit as x approaches a, some value of a, of a function. If that answer is very, very large, or it increases without bound, we say that it's plus or minus infinity. So as x approaches a, y goes to, or f of x in this annotation, y or f of x goes to plus or minus infinity. So all that I'm saying is x moves closer and closer to a, y increases without bound. And it may beg the question, well, what happens at a? Well, at a, the function does not exist. So when infinite limits do not exist, we generally use the notation plus infinity or minus infinity to convey that the function grows without bounds. So the second class of limits that we'll work with primarily in chapter 2.5, but I do want to briefly introduce them here, are limits at infinity. And a limit at infinity happens when x grows without bound. So the independent variable grows without bound. So when x goes to plus or minus infinity, with regards to some function f of x, if that equals some value, then we say that this is a limit at infinity. And if you look at this diagram, as x grows without bound, this function y over x squared is getting closer and closer to 0. And we can look at the table. As x grows very, very large, 1 over x squared gets very, very small and gets ultimately as close as it can to 0, but never actually equaling 0. So that's a limit at infinity. And again, we'll do more with them in chapter 2.5, which is the second test material. Oops, a little too fast here. So just as with finite limits, we still need to look and work with both left-sided limits and right-sided limits. And by convention, if a left-sided limit, we already know, equals a right-sided limit, then the infinite limit, and this is similar to a finite limit, then the infinite limit is said to equal plus or minus infinity. If the left-hand side and the right-hand side limit do not equal each other, then we say the infinite limit does not exist. But understand that plus or minus infinity, right, is still a limit that doesn't exist. But by convention, if they're not going off into the same direction, if they're not growing in the same direction, then we say that the infinite limit does not exist. So I want to turn my attention now to vertical asymptotes. And when we discussed rational functions in algebra or pre-calculus, we said, well, a vertical asymptote is a place where the function is undefined. And what kind of functions do they usually pertain to but rational functions? So when we were working with rational functions, right, in general, we would find a vertical asymptote by setting the denominator equal to 0 and solving. And when we found that value for x, whatever it is, x equals a, we said that was the equation for the vertical asymptote. Well, now that you have this notion of an infinite limit in your mind, let's revisit it. So as x approaches a of some function, if that is plus or minus infinity, then x equals a is a vertical asymptote. And if we look at it graphically, you can see here that as x, if this is a, this is 1 actually, we're looking at two different values here, but 1. As x approaches 1, this function goes off to infinity. And that is by definition what a vertical asymptote truly is. So just a couple of slides of problems. This next problem just emphasizes this right-sided, left-sided limit, and I want to review it with the diagram because we're looking at 2 points here, -2 and 3. So the limit as x approaches -2 from the left. So if I come at -2 from the left, the function itself goes off to -infinity. If I approach -2 from the right, it also goes off to -infinity. So therefore, as x approaches -2, right, the two-sided limit is -infinity. The situation with the asymptote at 3 is a little bit different. You know, it still has an asymptote, but the limit as x approaches 3 from the left-hand side, so if I'm coming in to 3 from the left, the function goes off to positive infinity. If I come in from the from the right-hand side, it goes off to negative infinity. So the limit at, as x approaches 3, the two-sided limit, is said to not exist. But again, recognize that plus and minus infinity is also the concept that it doesn't exist. However, we don't write it like that, right? We indicate that this thing is going off in the negative direction as long as the left-hand side and the right-hand side limit conveys the same. The last thing I want to do on this pre-exposure is just do a little bit of analytical work here. I don't have a lot of space, so I'll do the best I can to evaluate these limits analytically. So the first one, we're asked to evaluate the limit as x approaches 2 from the right of the function 1 over x minus 2. So I'm going to pick a number coming in from the right-hand side, so just a little bit bigger than 2, but not equal to 2. So if I let x equal 2.00, 3 zeros and a 1, and plug it into the function, which is what we do when we evaluate limits. We go to the substitution method first, which is just substituting in. So analytically, I'm just looking at this, and the function is going to be 2.001 minus 2, which is 1 over 0.0001, and you can see that this is going to grow large in a positive direction. But the sign is positive. So it grows large in a positive sense because the sign of this is positive because you're always on the right side of 2. If you come in at the left side of 2, so we let x equal 1 point, let's put 4 nines. So we're coming in towards 2 but from the left hand side, and if I plug it in to the equation or the function, which is what we do, we substitute in, you see quickly that this is negative now. So the answer here is negative infinity, and the answer here is positive infinity. So the overall limit, or the two-sided limit, is said to not exist. So that's how we analytically figure out limits. The next one is a little interesting. We look at this and we go to substitution. If we were to substitute a number, you know, 0.000 or 1.0001, which we're coming in towards the right, you would get a positive number. But what's confusing, if you don't you know, the other problem was nice and neat because we had one up top. But up top over here, we have something different. We have a number, essentially. So let's just substitute in 1 and see what we get. If I were to substitute in 1, I would get 1 squared minus 5 times 1 plus 6, right? Which also equals 0. 1 minus 5. Oh, I'm sorry. 1 minus 5 plus 6. So this is equal to 2. So the numerator is equal to 2. However, the denominator is going to, as we get closer and closer, right, to 1 from the right-hand side, this thing is going to stay positive. Right? This is going to be positive. It's going to be 2 over 0.0001, which is still a very large number. So even though the numerator is not 1, but another polynomial, this limit, if we evaluate it analytically, is still going to grow very, very large and go to positive infinity. So that concludes the pre-exposure for infinite limits, and we'll do more in class.